Welcome to Draglines 101. This presentation will basically give a overview of draglines and the engineering behind them. The presentation is intended for not only mining engineers but also anyone with a non-mining background. What's my background? I've been working in the mining industry for 11 years now, namely in open cut coal operations. The main dragline areas have included the mine planning, such as reserving, mine design and scheduling, and some detailed studies. I've carried out numerous on-site roles and project works during that time. They've mainly been in the Bowen Basin. For example, I've been to 7 sites that have used multiple draglines, and I've also had a stint down in the Hunter Valley, which had 2 draglines. I've also carried out project works relating to draglines, including the ramp crossings, minimising rehandle, installing parallel low wall ramps, double pullbacks and fault crossing work. The software that I've used in relating to draglines includes Vulcan and the dragline sections in those, and DragSim and 3D Dig. If you haven't seen a dragline operating before, I've just got a couple of basic videos, so we'll just show those. So here you can see the dragline bucket being raised, filling the material, and then once it's full, swings around whilst hoisting the bucket until it gets to the boom point, and then essentially the bucket is tipped vertically and the material is spoiled out and the cycle is repeated. Again, another example of just from sitting inside the cab. Again, the bucket being pulled back towards the machine, filling the material, hoisting it, swinging around into position, and tipping the bucket out and spoiling the material. Why are draglines used? They are used typically because they excavate high volumes of material compared to other machines on a mine site. It can be as much as double. Although the capital costs are high, we're looking at probably 150 million for a machine, they generally move waste for the cheapest unit rate. So they're also very productive and cost efficient at elevating the waste. So compared to a truck and shovel operation, draglines tend to get the material from a lower RL up to a higher RL much cost effective and easier. How much dirt do they move? Depending on their bucket size and how many swings they make, draglines can move from anywhere from 10 million BCM to 25 million BCM per year. Except for the large class of shovels, this generally is far greater than a typical truck and shovel operation. Draglines typically uncover coal and therefore dictate annual coal uncovery rates. They are therefore generally seen as a critical machine on site. Who makes them? Well, historically there have been 3 main manufacturers: Bucyrus Erie, commonly called BE, and Marion, who are both now owned by Caterpillar, and P&H. What size are they? Draglines are generally sized by their rated suspended load in tonnes, or RSL, which is essentially how much weight they can safely carry. It is usually made up of the bucket weight and the rigging and the waste. Draglines range anywhere from RSL 95 tonnes to about 365 tonnes. The largest dragline ever made was called Big Muskie, and it had a 500 tonne RSL with a 170 cubic metre bucket. What are they made up of? There are a number of components that make up a dragline, but the basics are shown here. We start with the boom, mast and the A-frame, which is essentially used to support the load and carry the ropes. We've got the machine house, which amongst other things contains all the motors and gearboxes for the drag, hoist, swing and propel, as well as the operator's cab. We have the tub, which is used to support the entire machine and used as a pivot point for swinging. We have the walking gear, which is used for moving the machine from place to place. We have the hoist and drag ropes, which are connected to the bucket and used to maneuver the bucket throughout its cycle. And of course we do have the bucket, which is used to actually dig the material. So we go into a little bit more detail about the bucket. The components on the bucket include the hoist chains and ropes, which essentially control the vertical movement of the bucket. We have the drag chains, which control the horizontal movement of the bucket. We have the dump rope, which basically controls the tipping movement of the bucket. We have a spreader bar in there which separates the hoist chains for connection to either side of the bucket. We have the bucket arch, which increases the bucket strength by minimizing bucket flexing, and it also allows connection of the dump rope to the bucket for the tipping process. And we also have the bucket teeth, which is used for the digging and cutting into the material. So what is the basic movement of the bucket? As a dragline engineer, it is important to understand the basic theory on how this bucket is controlled. The bucket's center of gravity is forward of the hoist chains and is prevented from tipping by the dump rope, which is in turn connected to the drag ropes. Except for directly under boom point, there is always tension on these drag ropes and dump ropes, which balances the bucket in a horizontal position as shown on the left. This position is usually seen within the dig phase of the bucket cycle. Directly under the boom point, the hoist ropes are now vertical and there is no tension on the drag ropes and consequently the dump rope, which allows the bucket to tip vertically as shown on the right side. This position is usually seen during the dump phase of the bucket cycle. What is the size of the bucket? Draglines buckets are usually sized by their holding capacity in volume in cubic meters, which is they typically range from about 45 cubic meters up to about 130 cubic meter bucket. What style of buckets are there? We generally have two classes. We have lightweight, which is a scoop style bucket, and they're used in fine materials like sand, gravel and well fragmented material. They're generally smaller in size in terms of cubic meters, but they're usually used in high productivity systems as their design allows them to fill quicker, and also their lighter weight allows more waste to be carried and still meet RSL requirements. We then have general purpose and heavy duty, which are generally production style buckets, and they're used in the hard blasted material like sandstones or where blocky material is evident. Generally they are larger in size in terms of cubic meters, but this also makes them heavier, which may have an impact on meeting RSL requirements. How do draglines move? They move around by use of their walking gear and only move backwards. The feet, or shoes as they're known, rotate around an elliptical cam, and as the shoes are placed on the ground, the dragline tub is raised slightly and dragged along the ground. The shoes are then raised and rotated around to make another pass. Their movement is very slow, usually around 100 meters per hour, as you can see from this video. What are their limitations? Well, draglines are limited by a number of factors. Firstly, their movement. Due to their size and speed, they cannot move around pits effectively, so they tend to stay in specific areas. That is, they'll alternate between two close by pits. The position of the material. They can only move dirt within a limited extent. Generally, they're moving dirt sideways, so there is minimal flexibility compared to a truck and shovel operation. And also their specifications. They have limits on the reach of the bucket, the angle of the boom, the grade they can work and walk on, and their dig depth and dump height. So on screen here we've just got an example of the dragline extents. How do these limitations affect them? Well, as just seen, the slow movement of the dragline requires them to remain in the one pit. So the idea is to minimize any walking or positioning time during the operation. The dig and dump radius, the dig depth and the dump height all contribute to both the width and depth of the strip being mined, as well as the methodology used to dig the material. The position of the material being dug somewhat dictates the position of the dragline. Some key elements about this positioning are explained as shown. We firstly have overhanding, which is generally above the tub line, or underhanding, which is generally below the tub line. Overhanding makes it harder to position the bucket, which results in slower productivity, but it means the dragline does not always have to be on top of the dirt, which may be required from time to time. Examples of this might be flattening the blast profile prior to walking along the strip, or digging out ramps. However, draglines are generally designed to work best in an underhanding position. We also have the position when it's sitting. So we have generally three classes here. So we have an online, an offline, or sitting at the chop line. Online, which is essentially parallel to the high wall, allows shorter swings, which results in higher productivity, and allows better control when digging high walls, but it also limits the overall dig and dump radius. We have offline, which is generally 45 degrees to the high wall, which allows medium swing angles, which gives good productivity, but it results and it also results in a larger overall radius. And then we have the chop line, which is generally speaking perpendicular to the high wall, which maximize the overall radius, but the larger swing angles also lowers productivity, and it also makes it harder to dig the actual high wall. The angle of the boom also has an impact on the profile of the dump material or spoil, as shown. So whilst we might lower the boom angle, which gives us more reach, it also means we've got a lower payload, and it also means we don't have as much dump height to play with. Conversely, if we steepen up the boom angle, we have less reach, but we also have a higher payload, and we also increase the dump height. But of course, with doing that, we can crowd the machine. So generally speaking, the angle of the boom is the same as the angle of repose for the material that you dig. The dig depth and dump height affects the amount of spoil that can fit into the area available, known as the final spoil envelope. The size of this envelope dictates the amount of initial material the dragline can dig, and is referred to as the dragline horizon, and is expressed as height. So you'll see it be called 45 meter drag, DRHOS. This envelope needs to take into consideration the swell of the material, and it is also a good idea to add a safety factor to ensure there is room for unknown changes within the strip. Due to this, how many coal seams can they uncover? Well, due to the size of draglines, they are generally the most productive in areas with minimal seams and high heights of overburden available. An example of this would be a single seam operation with one blast horizon. However, the high heights do incur more dragline rehandle, which in turn lowers prime productivity. But since draglines are the cheapest dirt movers, this can somewhat be justified. Although single seams are better, they can and are used in areas with two or more seams to great effect. The same dragline horizon technique is applied as for single seams, but you must remove the coal thickness. So how does the mining engineering come into effect? The very basics behind the dragline engineering are pit design, spoil fit, cross-sectional analysis, which includes your dragline methodology, scheduling, implementation, monitoring, and reconciliation. So what's involved in the pit design? Generally, mid-term planning department have allocated a dragline horizon for the pit, which is based off both the known spoil fit of the dragline and the strategic planning, so etc. As an example, what coal uncovery is required. Once the dragline horizon is known, the engineer should complete a strip design using the appropriate planning, geological, geotechnical pit parameters. These include the strip width and length, the location of high wall and end walls, high wall and end wall angles, if there's any benches, ramp accesses for both the dragline and the coal, and if any fault location. After this has been completed, an initial spoil design, usually to the maximum specs of the dragline, is completed. Again, taking into consideration the various pit parameters like the spoil undercut angle, the spoil angle of repose, if there's any benches, and ramp locations, either central or parallel low wall ramps. The design is then broken up into blocks, usually by 100 metres, and the corresponding volumes for the waste and the spoil room calculated. What's involved in the spoil fit? The spoil fit compares the block of waste to the adjacent available spoil room. This allows a spoil balance to be established, which shows areas where spoil room is either tight or plentiful. It is then up to the dragline engineer to decide what necessary action is required to take. If the spoil fit is tight, for example, do they assume the dragline carries the spoil along the strip length, or maybe they reduce the dragline volume by taking additional pre-strip in certain blocks? Or if the spoil fit is plentiful, do they raise the dragline horizon to take advantage of the spare spoil room? This, however, also impacts coal uncovery. The process is usually iterative, as the spoil fit dictates the dragline horizon, so it's important to get the design as accurate as possible. What's involved in cross-sectional analysis? There are numerous ways a dragline can dig the dirt within a strip, called methodologies. So whilst the spoil fit shows that the dirt may all fit into the spoil envelope, the engineer needs to determine how much dirt the dragline actually digs and how many times it actually digs it. These dragline methods are not covered in this presentation, but for any dragline engineer, these are critical to the operation and should be known or learnt. Dragline sections in packages like Vulkan and DragSim are created to represent the dirt movement and are usually modelled on every block corresponding to the original design volumes. The amount of dirt, we've just got a quick example here of a dragline section. So the amount of dirt moved in square meters by any piece of equipment is represented as either prime of the original dirt or rehandle, any dirt moved more than once, and is expressed as a percentage. These percentages can then be calculated out against the corresponding block volumes to determine the three-dimensional volume moved by the equipment. What's involved in the schedule? Both the strip volumes and cross-sectional data are then usually given to the scheduling engineer in order to carry out a mine schedule. The mining schedule is a complex part of the operation and usually has its own engineer. This is not covered in this presentation, but for any dragline engineer, these volumes and percentages are critical to the operation and should be as accurate or representative as possible. Since the cross-sectional work is two-dimensional, it is hard to work out the true rehandle for the entire strip, as it does not take into effect additional rehandle from normal practices within the strip. Examples of this are additional rehandle from crossing a central ramp, moving from one in-pit bench to another, or exiting the pit. A software package like 3D Dig is an excellent simulation tool for working out these rehandles and also for visualizations. What's involved in the implementation? More often than not, dragline engineering is an iterative process for a particular strip. This is usually because the key stakeholders, people like the production personnel, management and superintendents, they all have an input into the operation of the machine, which includes the methodology, design and practicality. The survey data is updated, which could be the coal edge or the blast profiles, or there might be unforeseeable issues, that being that the pre-strip mightn't have dug to the correct horizon, there might be poor blasting practices, wet weather, unknown faulting or even failures. When all the design work is completed and ready for implementation, it needs to be communicated to the production personnel, so generally the superintendents and the operators. The usual way is through visualizations like plans and presentations. Another common practice is through real-time GPS monitoring software. There's packages like Aquila and Pegasus, where the engineer uploads the design files directly to the dragline and the operators are able to dig exactly to the design lines. What's involved in the monitoring? It's imperative that the dragline engineer follows the progress of the dragline during its operation. This includes monitoring the material moved, both prime and rehandle, and the location of the dragline, which is usually in reference to a block line, and the dig position relative to the design lines. The dragline engineer can then use this information to compare against the plan, whether it be the design of the strip or the actual schedule, and can make necessary changes. There are numerous software packages available that record all the relevant data on the dragline operation, like Tritronics and MROC. These reporting systems usually are on a shiftly basis, but there's also some packages that are now real-time. What's involved in the reconciliation? At the end of the dragline operation, it's always a good idea to review and reconcile on how the dragline performed compared to the actual plan. This will allow the dragline engineer to learn from the particular operation and improve on any future work. The reconciliation should include planned versus actual numbers, like dragline volumes, both prime and rehandle, any cast or dozed prime volumes, any excavator prime volumes, the dragline dig hours and non-operating hours, the dragline dig rate and payloads to ensure that they're not going over the RSL, and also any comments about the strip design or other problems that may have arisen during the strip operation. There's just another example of a reconciliation. We've just got a question here to go back to the dragline section. So I'm hoping that it's not too laggy. So in this particular example, we have the blast going off, then a bit of dozing, then the dragline comes on and will dig its key. In this case it's extended key, so the in-pit bench will be a little bit higher. They'll doze that material off. The dragline will then go up onto the in-pit bench and start removing its blocks pass, putting it into final spoil. And I believe that's the end. There's no more questions. So thank you for listening again.